Okay, I think it's time to get started. Hello, everyone, and welcome to today's webinar, hosted by Chemical Engineering Magazine and sponsored by Xylem and Evoqua. My name is Scott Jenkins. I am the senior editor at Chemical Engineering Magazine. The topic for today's webinar surrounds the water treatment that's involved in the production of blue and green hydrogen. So decarbonization of hydrogen production has become a real key global initiative. Most of the attendees out there are likely aware of two approaches to hydrogen production that are colloquially known as blue and green. Blue hydrogen production referring to the conventional steam methane reforming to produce hydrogen and coupling that with carbon capture and storage. And then green hydrogen production involving the coupling of electrolysis of water with renewable energy, aiming for a carbon neutral process. Both processes, blue and green hydrogen, require large amounts of water. Water must be treated prior to chemical and electrochemical processing, and also wastewater generated by the processes need to be treated prior to discharge. So effective water treatment for hydrogen production is essential for process success because on the front end, the water must be of the right quality and quantity, and on the back end, the wastewater must meet effluent requirements. But really, the overall sustainability goal is to reduce the demand for initial source water. So to take us through this topic in more depth, we have two speakers from Xylem and Evoqua, which, as many of you know, are now one combined company. So we're going to be hearing first from Juvencio Casanova. He's the customer vertical director for the chemical process industry for Xylem and Evoqua. He's an accomplished strategic business executive with extensive global engineering and commercial experience in the energy, oil and gas, and petrochemical industries. He has a bachelor's degree in chemical engineering and an MBA from Texas A&M University, has over 20 years of experience delivering solutions for the energy, oil and gas, and petrochemical segments in industrial water management, sustainability, and ESG initiatives. He has direct and global experience with customers, including super major petroleum companies, national oil companies, independents, and international companies. Juvencio leads the hydrogen initiatives for Xylem and Evoqua. And then also, we're going to be hearing from Kishore Nair, a Houston-based business developer for Xylem and Evoqua's heavy industry division. Kishore holds a PhD in mechanical engineering from MIT, a bachelor's degree from IIT Bombay, and he's a licensed professional engineer in Texas, a former industrial water entrepreneur, a Forbes magazine 30 under 30 figure in the energy category, and a U.S. government recognized global expert on industrial water and energy water nexus. He is one of the EB1A Einstein Visa awardees. So Kishore has authored 19 technical publications and is listed as an inventor on 3 patents. He has 11 years of experience in designing, developing, managing, and selling industrial water solutions across academia, startups, and large corporations. He also has strong management experience leading multidisciplinary teams in nonprofit startups and large corporations. So our plan for today's webinar is going to be to have Juvencio and Kishore present their slides for about the first 40 minutes or so, and then we're going to follow that with a live question and answer session. So if you have a question at all for the speakers during the presentation, you want to go to the Q&A tab, which is on the right side of your screen, and just type in submit the question from there. And after the presentations are finished, we'll get to those questions as they come in. I wanted to remind everyone that the program is being recorded today, and it will be archived for rewatching. It's going to be at www.chemengonline.com/webcast. There'll be a link there to watch the webinar again. and I'll remind you of the link at the end as well. But with that, I'd like to turn the program over to our first speaker. So, Juvencio, please go ahead.
Thank you very much for the introduction, Scott, and good morning, good afternoon for everyone that's joining us. Appreciate your time. And as Scott mentioned, we're going to be speaking over the next hour about water solutions within the blue and green hydrogen space. I'll start with a brief introduction on our organizations. Some might know us as Xylem, some as Evoqua. We are now one company. We still remain committed to our customers in the water and industrial space, and we will continue. For anyone who's worked with us in it, bringing innovations and proven and unmatched services to the water treatment industry. Today, I'll be reviewing with Kishore the following topics. We'll start with an introduction and market. We'll start then talking about blue and green hydrogen specifically, and following that, more specifically about water treatment when it comes to the hydrogen production. As Scott mentioned, I am the vertical director for our chemical processing industry. And as many know, hydrogen production has traditionally fallen into that category of industrial gases and chemical processing. So I'm leading at the moment with the Evoqua team and the Evoqua Silent team the strategy for hydrogen. So I'll get us started. And where is the hydrogen? Where's this an exciting time for what is happening in the industry when it comes to energy transition? There are several drivers in play that are making an impact on why hydrogen is becoming a very hot and popular topic. For example, I'll start with sharing the Evoqua Xylem sustainability goals. Many organizations are implementing both self-imposed and obviously mandated by some legislation. And Evoqua is committed to reducing our footprint of water usage, carbon intensity, as well as use for fossil fuels. And that's what we think about our footprint. We also have an impact on the handprint, and that's most of the topics we'll discuss today is about how is Evoqua supporting hydrogen companies, producing companies, in making sure they're meeting their goals for hydrogen production. If we think about where hydrogen is today and how the industry is looking at hydrogen in the future, there are several ways of making hydrogen. Kishore is going to dive deep into those details. High level, hydrogen is going to be seen in the future as being part of an energy, about part of the energy mix. Today is being used in refining processes, ammonia, other chemical processes, steel. There is a great potential for hydrogen to penetrate into different markets for transportation, synthetic fuels, ammonia, continue that, but at a higher level. And all this can be done with a hydrogen that it's clean. You will hear blue, green, purple, different ways of hydrogen. We like to call it clean hydrogen because essentially what's happening is we're bringing in a product that is um, carbon neutral, carbon free. Move on to the next. If we explore a little bit more, what are those market drivers, and we look at the what really accelerated significantly the hydrogen production projects is the Inflation Reduction Act. That clearly, after the announcements were made, clearly that laid out a strategy, that policy for many companies to start diving in and getting into the hydrogen space. The DOE estimates that by 2030, clean hydrogen is going to be going into about 10 million metric tons a year. By 2040, another 20. By 2050, another 50. This is new clean hydrogen into the market. Today, it's about 150 million metric tons. So again, Kishore will talk about that, but at a high level, the next decade is going to be very important and transformative for the hydrogen industry. And it's going to depend on how much hydrogen can be part of the energy mix. Industrial processes, as I mentioned, use it today. But if hydrogen can really become into new and emerging concepts such as transportation and electricity generation, energy storage, which has the potential and can be done, and the technologies are well known, then hydrogen is going to have a really big impact and in the next 20, 10, 20, and 30 years. Now, clean hydrogen is going to be facing some headwinds, of course, some tailwinds. Um, what we see today as very positives for hydrogen production, or this clean hydrogen coming into the market, global decarbonization that is driven by ESG clearly is what really made hydrogen take off as a viable solution. The Inflation Reduction Act, as I remember, we have existing market and existing applications for hydrogen today: ammonia, refining, and other chemical industry. So those are well-known, established markets that clean hydrogen can be replacing. And of course, as those markets grow, it can be taking its place. Feedstock is stable and it's scalable. One key, very key, why hydrogen is seen as the most important clean energy for the future. It's because of that stable and scalable part of the feedstocks that are going into hydrogen, in particular natural gas, decarbonized, and then for green hydrogen, it's clean water. And within the technology, renewable energy and lower cost for electrolysis, in particular for green hydrogen, that is helping the industry as well significantly. And of course, like everything, it will have some tailwinds. A scalable, renewable capacity, the applications and the stage and the transportation, the thermodynamics of power to X, and obviously the quality of the water required. That's going to be also um, a headwind for the industry. I want to close this market and introduction with with a slide that is picturing stressed areas on the right, water stressed areas in North America. This If you can see that the red spots are the highest stress water areas in North America, in the U.S. pretty much. Um, and on the left-hand side, you can notice that those are announced projects for green and blue hydrogen. The blue areas are for the blue spots are for blue hydrogen. That's going to be mostly in the Gulf. The Gulf is going to have the market for the Gulf of blue hydrogen is going to be typically replacing and increasing the new markets for industrial users, refining, petrochemical, and ammonia. They're also close to ports. They're also close to pipelines. So that's why we see a significant amount of blue hydrogen in that region. Green, it's a little bit more segmented, fragmented across different regions. In particular, the West is seeing some. There's a few reasons for that. That's where we have renewable energy, large spaces for solar, wind across the center of the North Texas and across the center of the US. Also some renewable energy. Here's what I want to have the takeaway as we are all participants in the industrial water market. The stressed areas towards the left of the countries are going to see large amounts of projects for green. The Gulf as well. The one questions when we talk to our customers and the hydrogen producers is when they're selecting a geography, a region on where to have the plant or production facility for hydrogen production, they talk about energy, renewable energy in the case for green hydrogen. They talk about, as I mentioned, ports and close to the customers and pipeline for blue. They talk about other being close to the end customer, their offtake, or where they're going to be selling that hydrogen. There's typically one question that is, or one answer that is maybe third place. which is the quality and accessibility of the water. And that's where we want to dive the conversation a lot deeper into this next 40 minutes, because that is really key. Again, hydrogen, in the case of green hydrogen, water is going to be the feedstock for an electrolyzer, which is going to make the hydrogen. And the importance of having accessible, clean, and water that can help meet the standards and the ultra pure water qualities to make that hydrogen are very important. There's going to be challenges in the industry as producers come into play and start looking and finding the locations for their production plants for hydrogen. And water is typically being asked third. We want to help our the industry and our customers have that question elevate a little bit. It's going to be challenging, but there's no technology at the moment that can be met to meet your quality and the ultra pure water quality needs for hydrogen production. In the case of blue, it's more in the quantity, right, and scalability, because of blue is going to be participating in large industrial facilities. So that requires large amounts of water treated at a particular and high quality. So that is the reasons why we want to dive deeper into the conversation of how to treat water sustainably to meet the needs of hydrogen production in the next 30 to 50 years. And with that said, I'm going to pass it on to Kishore so he can dive deep and explore into water treatment for hydrogen production. Take it away, Kishore.
Thanks, Evencio. We'll dive in now more into the technical aspects of both blue and green hydrogen and the water treatment associated with that. Firstly, let me start defining some things and bringing back some topics from Evencio's slides. So people talk a lot about the different colors of hydrogen. I want to define them first before we dive into who uses hydrogen today. So broadly, if you look at the first diagram I have, the first three are how largely we make hydrogen today, mostly from gray hydrogen, which is steam methane reforming, without any carbon capture or storage. So that's directly from natural gas, and and some more from coal, either black or brown. And what we'll be talking more and what's more relevant in the US is blue hydrogen and green hydrogen, which is the first is steam methane reforming with carbon capture and storage, and the green is water electrolysis with renewable energy powering the electrolysis. And we'll dive more into those. Um, Pink is not talked about a lot, but that's when electrolysis is powered by nuclear energy. Now, what I did want to dive in is understanding who are the major users of hydrogen today. And there's both pure hydrogen, where you need hydrogen in a pure form, and hydrogen that is provided along with some other gases. The first column here are pure hydrogen users, and the second column here, those are when hydrogen is used along with another gas like carbon monoxide and syngas. So largely, the largest users of hydrogen today is refining for hydrocracking and hydrotreating. So that's breaking the complex hydrocarbons to smaller hydrocarbons. Then you need to supply hydrogen to complete the chain, and for hydrotreating for refining high sulfur oils. The other major user of hydrogen, where hydrogen is needed in a pure form, is ammonia production, the classic Haber-Bosch process. If you look at hydrogen along with another gas, in most cases syngas here, that would be methanol production, followed by iron and steel production, where DRI stands for the direct reduction of iron. So this is one major user of one other user of hydrogen that would become more relevant in the coming years. Now, I want to also address how is it made today, and this is data from the International Energy Agency from 2019. About 75% of global hydrogen production, of pure hydrogen production, came from natural gas. About 23% came from coal gasification. This is mostly done in China. And about 2% was attributed to both oil and electricity. I believe most of that was electrolyzers. That number may have gone up to about 3 or 4% now. Uh, and I've shown below the main reaction pathway used to make hydrogen today, which is steam methane reforming from natural gas. And we'll talk more about this at the end of the presentation when we discuss blue hydrogen. Is just a diagrammatic representation of green and blue hydrogen. Green hydrogen, you need renewable electricity, powering an electrolyzer, and subsequently you need storage and transmission infrastructure for the hydrogen. Um, Blue hydrogen is the same process, the same process as what's conventionally used, but the carbon dioxide that is produced from the process would be captured and sequestered. Now, I wanted to talk more about firstly where the costs of hydrogen lie, and this is from the International Energy Agency reports for 2019, I believe. So if you look at it, hydrogen from steam methane reforming, it's about dollar point two a kilogram, making it today. Blue hydrogen, they estimate it to be slightly more expensive, and green hydrogen much more expensive with a wider range depending on electricity costs and other aspects. So this is where the 2020, so the recent Inflation Reduction Act played a big role, because the tax credits range from about 60 cents to $3 a kilogram of hydrogen, and that is enough to make green hydrogen competitive with existing market prices. And the thinking is that over the 10 years of the tax credit duration, the cost of production of green and blue hydrogen would reduce sufficiently. Because anytime a new technology doubles in production, the overall costs reduce about 15%. So over 10 years, the expectation is that a lot of the costs would come down for green and blue hydrogen, not too different from how costs have come down for solar cells over the past 20 years. But the current opportunity is driven by the Reduction Act. Just wanted to highlight how important that is as a project driver. And now I want to talk about the water demand for hydrogen, which is not talked about often. Stoichiometrically, I've showed what's on the left. So if you use the actual reactions and stoichiometrically account for the mass of hydrogen required, this is what you would see. It's not a whole lot, but the problem is these processes do not directly happen just with the stoichiometric reaction. There's a lot of other processes around it, with cooling of the electrolyzers, for example, and cooling towers and blue hydrogen processes. Um, those consume a fair bit of water as well. So once you account for overall water usage, the demand for water is significantly higher. So this is on the same scale. Once you account for cooling, it goes up a whole lot, and this includes both international project data and some of our own data from ongoing projects that we have. In some of the green hydrogen projects are even higher than 25. I think 27 was one. 20, it can go closer to 30 even in certain scenarios. uh, Blue hydrogen generally consumes less water. In the US, I would say the number is more numbers between 10 and 20 we have seen for blue hydrogen. Green hydrogen consumes more water, both stoichiometrically and because of the additional cooling requirements. Um, Green hydrogen does require more water, and this is becomes more important because if you remember the plot that Juvencio showed about water stress regions, um, cooling water also requires some amount of treatment. And in many projects we've seen that the cooling water component is a major cost driver when the water quality isn't great, because then you need to start using membranes and other things to even meet the cooling water quality, especially when folks use groundwater. So this is a major factor that can drive costs on the water treatment side in several projects, and I wanted to highlight that. Now, I want to dive a little bit deeper into green hydrogen. So there are broadly three types of green hydrogen electrolyzers. Alkaline electrolysis, where you have an alkaline material, sodium hydroxide or potassium hydroxide. Generally, it's potassium hydroxide as the electrolyte, and a diaphragm that separates the two gas streams, and the ions move through them. So this is the traditional way of electrolysis. This has been around in commercial for about 100 years. The current densities aren't very high, about 400 amps per centimeter square. the technology that's come up a lot recently is polymer electrolyte membrane electrolysis. So instead of liquid electrolyte, you have a polymer that is conducting the ions through. This allows the system to operate at much higher current densities and uh, and 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 be more provide hydrogen on demand in a way. So this is very good to couple with a renewable variable electricity source. And we're seeing a lot of projects come through using the PEM technology. And the other third technology is solid oxide electrolysis. Now this is something that's still early in development. There are some projects that are showing up now. The other two, there are actual commercial projects being planned and deployed right now. Solid oxide, it's still a little bit earlier in the piloting stage. I believe the first commercial larger scale units just got operational about a month or two ago in the world. So this operates at much higher temperatures, because at higher temperature the voltage barrier is lower and you can get much higher electrical efficiencies, but at the cost of thermal energy. But this promises to be more energy efficient than the other technologies. Now at the bottom I've mentioned water qualities here, and this is uh, a typical water quality standard that has been used by several electrolyzer manufacturers. This is the ASTM reagent water grades. Type 1 being the most ultra pure water. It's almost semiconductor grade water. 18 mega ohm resistivity. There's literally nothing, almost nothing in the water. Uh, and ASTM Type 4 has more TDS, more conductivity. Type 3 is a pretty common reagent grade that we've seen now show up in several projects. So typically, alkaline electrolysis doesn't require as good water quality. PEM electrolysis definitely needs much better water quality, and we've seen projects going from Type 1 to Type 3 water quality. Alkaline electrolysis can take a little bit it's not as it's a little bit more forgiving, especially on silica levels. Solid oxide electrolysis, it's similar to steam generation. So I would assume that the water quality would be typical to boiler feed, ultra high pressure boiler feed quality. But the specs have not been published very widely. Um, so I didn't want to give a number there. One number I did want to call out is uh, the rough number is for every megawatt of electrolyte of green hydrogen electrolyzer, you need about 1 GPM of makeup water that is produced by a water treatment system. The projects that we've seen today are more smaller scale, from the 20 to 120 and the early hundreds of megawatts. And we've steadily seen the progression as the Inflation Reduction Act has come from smaller projects to bigger projects. We expect projects greater than 1,000 megawatts to also happen in the coming years. Um, Now that I've established um, the need for a high water quality requirement for some of these electrolyzers, now let's look at how we actually achieve a good water quality. So this slide summarizes several different technologies that we use to get to a good water quality standard. Uh, Starting off with with media filtration, and one other step I've not shown here is oftentimes we need to use clarification if it's raw water, for generating cooling water and other needs. So broadly, we take it through smaller and smaller pore sizes to get to the purity that we need, and we shift to a different technology platform as well towards the end to get to that really ultra pure water quality. So media filtration or multimedia filtration, that removes particles more than about 10 microns. So microfiltration even lower than that. We remove first the large particles, the suspended solids, the bigger molecules. Ultrafiltration is another technology that's become sort of the gold standard if you want to end up producing water that goes into an RO. Its pore size are about 0.02 microns, and we can remove almost all of the suspended solids, but not the ions. There's nanofiltration, which can remove a lot of the divalent ions, and reverse osmosis, which removes most of the ions, not 100%, but in the high 99% or 98% for certain constituents. And you're left with water at the end of let's say two passes of reverse osmosis that still has some monovalent ions that needs to be polished further, and that's for that we use a technology we have called continuous electro deionization, which I'll be explaining more. The other technologies are fairly different versions of barrier technology, either media or a physical membrane barrier. Continuous electrodeionization works on a very different principle, and so does mixed bed deionization. I'll be talking about that in the next slide, and these technologies will become relevant as I share the water quality that you get as an output at each of these stages. So very briefly, what is continuous electrodeionization? It's a coupling of two different technologies, an electric-driven water treatment technology called electrodialysis, and it's some things there are certain similar principles to even electrolyzers there, and typical mixed bed ion exchange sort of resin-based technology. So there is a positive and a negative electrode that drives ions in different directions. Feed goes in. There are membranes that are charge selective. So they let the positive. So one of the membranes will let the positive ions go through, but not the negative ions. So what happens is the one of these channels gets concentrated while the other gets diluted, and the ion exchange beads in there provide high enough conductance in the water to allow for the ion transport. The electrodes make H plus and OH minus ions that allow the regeneration of the resin there itself, the resin bead in situ. So this doesn't require additional chemicals for regenerating the resin beads. It happens within the process. So folks who are familiar with mixed bed deionization, this is a chemical-free approach that we do use in our processes to get to ultra pure water. This one will become very clear in the next slide when we talk about a typical process of taking, let's say, municipal or river water. If it's river water, we would directly go send it through UF if producing electrolyzer water grade is desired. If it's municipal water, we'd start with multimedia filtration to remove any excess polymer, send it through RO, then continuous electrodeionization, and possibly mixed bed ion exchange as a final polishing step, depending on the water quality. Now, what does that look like? So the media filtration would remove the suspended solids, and UF the same. At the end of two passes of RO, we can take this is typical, let's say, on the high end of municipal water and river water, 500 ppm of TDS gets reduced to 5, which gets reduced further down to 0.01, and up to about 17 mega ohm electric resistivity at the end of the CEDI process. And then mixed bed ion exchange gets it to ASTM type 1 quality for this particular case. We can even get to type 1 quality even with the CEDI by tweaking the different membranes we have in the RO system. But this is one approach we've used to get to type 1 water quality. Type 3, we wouldn't need the mixed bed ion exchange. We can get there very easily with type 1 and type 2 with just the RO and CEDI. But this sort of gives numbers to how we can get close to the ASTM type 1 standard required by several electrolyzer manufacturers. Now, this is a block flow diagram that shows the overall process with multimedia filtration. In this instance, it was municipal water going in. We were making two-pass RO. We're sending the reject of the two-pass RO back to the front of the system that allows us to operate at higher recoveries. There's a nitrogen storage tank, nitrogen blanketed storage tank to make sure that there's no dissolved gases that make into the pure water stream. And we polish with CEDI, mixed bed, and to control for biological growth, we also use a combination of ultra UV radiation and cartridge filters to get to certain biology specs that some manufacturers also have. So roughly 1 GPM makeup water for 1 megawatt electrolyzer, 1.5 GPM feed water per megawatt electrolyzer. Now, switching gears, I'll talk about blue hydrogen really quickly to explain what is the steam methane reforming process. Natural gas reacts with steam to make carbon monoxide, which is used to make carbon dioxide and hydrogen. So the carbon dioxide is the byproduct that needs to be stored, captured and stored. I want to talk about autothermal reforming as well. SMR or steam methane reforming has been the majority process. About, I believe, as of 2019, most of the world's hydrogen came from the SMR process. But some of the newer blue hydrogen projects are shifting to autothermal reforming, where there's this partial oxidation step of methane or natural gas. The thing is, SMR is an endothermic process. It requires a lot of heat. The temperature, the reaction started at about 700 Celsius, I believe, and to maintain that requires a lot of heat. The autothermal reforming process uses the partial oxidation of methane to heat the process and keep it going. So that way you don't need a separate thermal energy source. Or if you do, because of inefficiencies, it won't be a lot. Um, we are seeing new blue hydrogen projects using the ATR approach. Now, I want to talk about one of the challenges, and if there are blue hydrogen developers listening, I want to mention this aspect of which can be a challenge and drive costs in your wastewater treatment. One of the side reactions that happen in the blue hydrogen or SMR process in general is there is nitrogen impurities in the gas that can react with the hydrogen to form streams that you wouldn't want to form, like hydrogen cyanide and formic acid. Now, what happens is once cyanide crosses 1 milligram per liter in the final plant's wastewater, that'll stop the degradation of ammonia, like sort of the first step to wastewater treatment, and that can give conventional wastewater treatment plant designs a lot of problems. They're largely insufficient in the conventional design cases. Now, what we've done is early engagement on projects, on blue hydrogen projects, to bring up this issue. It's something easier to tackle in the design stage and to minimize the production of cyanide in the process itself, and the choice of scrubbers and the relative mix of streams relative to cooling water, which will also blow down, which also ends up in the wastewater stream. Um, One other step is possibly is the pre-oxidation of the cyanide in a sub part of the process. We have uh, alkaline oxidation ways of oxidizing cyanide in smaller streams. We do have our own proprietary ways where we have designed biological treatment solutions to manage a higher threshold of cyanides. But what we recommend is an early engagement between the water treatment and wastewater folks and the internal process designers to minimize some of these problems right at the get-go. It's much more expensive to tackle it, to leave everything to be tackled at the wastewater stream segment. So I just wanted to mention this early in this process, because this is a challenge that we have seen on some projects, and we've helped developers make decisions along the way to mitigate some of these cost challenges. Now, I just wanted to quickly summarize and what all Evencio and I have spoken about. We've introduced the topic of, or defined what is blue and green hydrogen. We've shown you that tax incentives are driving this current demand for hydrogen, and that the distribution of the projects across the U.S., a lot of them are coming up in water stressed areas where both water quality and water availability are key challenges. Green hydrogen projects will need more water and more water treatment. Blue hydrogen projects, the wastewater treatment is a challenge, and that's where there are significant technical hurdles to cross. Uh, Green hydrogen water treatment, ultra pure water is required across most electrolyzers, and there are different technology choices that need to be made along the way to drive costs to a minimum. We discussed the overall cost of hydrogen and the water consumption specific numbers, and we also discussed the technologies needed to get there. And with that, it's time to take questions as a team here. And thank you for your attention, and we look forward to answering your questions. So back to you, Scott. So.
All right. Yes, thank you guys for the presentation. That was excellent. And we do indeed have quite a few questions have come in already. Just to remind everyone, if you have a question, to use the Q&A tab on the right and type your question in. And also wanted to remind people that to the right, you'll see a tab for handouts. Evoqua has provided some resources for people to reference following the webinar. So make sure you take a look at the handouts there and see if there's anything of interest there. So I'd like to start out with this question here. So if we look out to the long term, what do you think would be more common, the blue or green hydrogen, and if you can just tell us a little bit more about how they, like where they fit in the grander scheme.
I'll get started on that one. Thank you for that question. As I was introducing the topic, we talked about what are the likely places where blue and green were going to take place. The answer really is blue is going to help decarbonize the industry large scale when it comes to being replacing some of the hydrogen used for refining petrochemical and ammonia methanol usage. And as that blue hydrogen is replaced, green has its space within the smaller segments and closer to customers that are more niche, fragmented. For example, we're seeing that California has a strategy around transportation with hydrogen, and therefore green is going to regionally be taking place. As far as being more popular, blue can help the industry transform and have its place for hydrogen in the energy mix. And that's going to be key for hydrogen. If hydrogen can go in and replace transportation at a scalable and significant level, if it can replace electricity generation, blue can help with that scalability at the beginning. As technology, cost, and the use of hydrogen increases, green can help that growth as well. So it's going to be a little bit unknown over the next 10 to 15 years will be key in where the hydrogen is going to be, which of blue or green is going to be used. At the end of the day, the hydrogen needs to find its use in the market, and the more hydrogen is used as part of the energy mix and in the other industries I mentioned, the more both of them can help, and green can significantly help the overall, if it's about decarbonizing when it comes to using less fossil fuels, that can help, of course. And for sure, Kishore can add some comments.
Okay, go ahead, Kishore.
Yeah, no, you went to got it right. Like there's economies of scale with blue hydrogen. Those will be bigger projects. We already have seen that there's generally a preference for blue hydrogen in the U.S. Gulf Coast. Green hydrogen is more uh, can come in more smaller form factors. So if you want to fire up the hydrogen required in all the warehouses in Amazon, Walmart, the fuel, the the the, the forklifts use hydrogen to power them. For their green hydrogen makes a lot of sense. For example, um, so broadly, I think it'll go in two different trajectories as what Evencio mentioned. And over 10 years, costs will come down a lot in green hydrogen, I can see, because a lot of it is material costs. So some of that will come down and maybe more decentralized production.
Yeah, one key item is that green hydrogen is using renewable energy, solar, wind, and there are still challenges of capacity, for example, in the United States. So those challenges remain. However, as renewable energy is more, again, part of that energy mix within the industry and within the markets, green can pick up its pace. One comment too on blue versus green. Most of this discussion is within US, North America. Globally, probably should have mentioned that at the beginning. Globally, Europe, Australia have significant and large projects around blue and green. In particular, green is far more advanced than the US, with policies and other projects that have already come into market, are already operational for clean hydrogen production.
All right, great. Thanks for that. Next question here is, how challenging is it to maintain ultra pure water quality for green hydrogen, and what goes into it?
Yeah. So that's a good question. It's not just the technology. There's also a pretty strong operational component to it as well. In some of these technologies, biofouling is something that needs to be prevented a lot. So it goes down also into the piping design, how many bends you have or you don't have, and how close the electrolyzer is to the makeup water source, and how frequently do you sanitize the lines. There's a significant operational component to it as well that we have figured out in decades of semiconductor water treatment, where the water treatment centers are in some cases even more stringent. So it's not just the capital, but how you use the capital with trained personnel and operations and maintenance procedures. It's a There's a lot more art than science also in some of this, and that not too many people sort of. It's something that is less understood and less valued by the general engineering community, because folks don't realize the operational challenges involved in getting to those and maintaining something like that for 20 years of a project. But there's a lot of operational aspect to it too. So and yeah.
All right, great. So next question here. So the question says, isn't water for utilities mostly conserved and used in a closed loop? So to what extent is it really consumption?
Yeah, so that's a good question. So that's why I use the word water demand here. So that's the water that these projects need. Now, water consumption, that's a little bit trickier to answer, because in the West region, we have seen some of the projects, they, they, they they need evaporation ponds to deal with the wastewater or the brine discharges, because there's not a good way to recover it. So it's not easy to tell how much of this that was water usage or water consumption, which is like water completely like lost to evaporation, for example. It's a little hard to call that out, and that's why I chose water demand, because that's an easier metric to measure across projects. Because down here in the U.S. Gulf Coast region, most of the streams that are generated would end up back in the river water, so the water usage would be, or water consumed would be lower overall. Like the water withdrawal would be lower, but the water demand that goes into these facilities, that's what this captures. And the other question, I would have loved to talk about it more, but it's such a huge variation across projects and across regions that it's pretty difficult to capture here in a single image. And I saw several questions on that theme, so I wanted to thanks for bringing that up, and I hope this answers that question. So yeah.
Yeah, and there's actually a kind of a follow-up a little bit in some ways to something that you mentioned already. Is the next question is, does the water demand for cooling tower um, correspond to evaporation, or in other words, water that can't be reused, or is that water usage in total?
Yeah, so this is water that is going into the facility. Not all of that gets evaporated across, but I would think that uh, let me think about that. Like the cooling water loops are much higher. Um, I would think this includes the cooling water evaporation is probably a big component of this as well, because the this this is the net water going in, so there
Yeah.
is a significant amount lost to evaporation as well. So yeah.
As you see, there's a variation, right? Because cooling is an important part of the processes, not just related, not for the hydrogen production itself, but the utilities
Yeah.
involved in it. And when we typically talk about water used for cooling as a utility, it's the makeup water, right? It's the water that you need to continuously replace, either because of evaporation or if you have to do blow down because of the quality. So it's accounting the water that, as Kishore mentions, needs to go into the plant to make up for all the processes and use the water as the utility. Thank you.
All right, great. So next up is a question about water quality grades. So the question says, I understand that the water quality grades types 1 to 4 are for the feed water for electrolyzers. So the question is there a minimum quality for cooling water in the electrolyzers? So like a minimum quality standard.
Yeah, so that's mostly determined by the metallurgy used for the cooling towers. There's a pretty good standard on that. Like after a certain level of chloride, it's very corrosive to cooling towers. So what we found a lot in when groundwater is used as the water sort of source, the salinity of the water and the chloride levels are too high for conventional, typical cooling tower metallurgy. So, so oftentimes we've had to put in a reverse osmosis system to treat that groundwater down to a level that is not corrosive for cooling towers. So we have seen that be a big cost driver. The cooling water treatment uh, being a bigger cost in some cases in some projects, just because those systems are bigger than even the ultra pure water loop. Um, and that really depends on region. In the Gulf Coast here, river water is pretty good. You can send that into a cooling water. So for that, you only need a clarifier. But when it gets to groundwater and salty surface waters, then you need an RO to treat that down to a level that you can send into a cooling water. So it's less of the cooling water requirement of the electrolyzers than the cooling tower metallurgy that determines the quality needed. So.
Yeah, so I'll add that Kishore brings a good point when he talks about the water as we see these green hydrogen projects come into play. I was mentioning at the beginning that the selection of the geography of where the green hydrogen is going to be produced is near a renewable energy. For example, it can be solar or it can be wind. Well, guess what? Solar is in places where water is relatively scarce, or stressed water. Let's say it's stressed water, and that's when you start thinking about, and we start finding water that is very the quality is not very good, and then it needs further treatment. For an industrial process, for example, we'll give the example of something in the Gulf Coast. If it's a petrochemical plant, it's taking surface water from a river. Clarification, multimedia, ultrafiltration is becoming very popular, and because of the advancements in technology, so we could filter water from a river, for example, pass it go through an ultrafiltration system, and that ultrafiltrated water can go into a cooling system. So that can be a typical application for cooling, and of course, all of this in the context of hydrogen. Now, after it goes into the cooling, obviously you have all the chemistry, 5 to 7 cycles is common, and then the water needs to be treated. What we're finding and what we wanted to highlight is the water, the geographies where especially the green hydrogen projects are being developed are areas that have stressed water, and the quality requires extra steps than a traditional, let's call it, ultra filtered water for cooling process. So those are key differences we're finding in the industry right now that are important to highlight.
All right. Next up, we have for a given electrolyzer technology, let's say alkaline, what leads to the need for such different water grades, the like ASTM 234 for the alkaline electrolysis?
Yeah, so the different manufacturers have slightly different ways they're doing these processes. So even within technology groups, we've seen slight differences. Uh, but broadly, the difference is mostly based on the type of technology. So alkaline, just because of the nature of how it works, the lesser chance of biofouling. It's more of a purity aspect of how pure of hydrogen do you want to produce that dictates some of that. The PEM systems are more, biofouling is a bigger concern, so they need purer water and sometimes even biology specs to make sure that the water is, doesn't have anything that can foul membranes. Um, so there are different considerations, and even within these technology groups, we've seen different design philosophies that different electrolyzer manufacturers use. But broadly, it's purity of hydrogen and uh, fouling concerns that I think drive some of these choices. So.
All right, we'll take another one. And so I think if I'm reading this right, the question is, does the continuous electrodialysis risk, I think, potentially
Yeah.
introducing chlorine or sodium ions in the electrolyzer feed water, and therefore introducing a potential impurity in the hydrogen.
No, I wouldn't think that would be the case, because it's the way it does is it takes the higher conductivity water and reduces it by the time it goes down the length of the channel. So it gets to really high purity there, just by how the technology works. So I wouldn't think that risk is um, significant there, because it reduces those constituents in the water overall. Sometimes we do use this mixed bed system at the end, just for in certain cases, if the water is of higher TDS, because a lot of the projects do have groundwater in it, and it's much higher TDS than what I'm showing here. So there we've had to use different RO membranes, and the choice of the different technologies becomes more critical to get to that ASTM type 1 standard. So we've not had a problem with that so far. There are other factors at play. The CDS systems typically need a good building around it, climate control, and it does a great job overall. But depending on where the project is, and how they want to construct the project, we go with different designs, and also how close this is to our regeneration facility. A bunch of choices that we have to make when it comes to projects. So it's very project specific, those choices, but broadly that's not a major concern, so it shouldn't be a problem. But
All right, very good. I'd like to just bring up another question, or another topic, actually, seawater electrolysis. So
yeah.
there's a question here talking about, can you talk a little bit more about seawater electrolysis and the challenges behind using that? And then followed on that is, how does the cost of byproducts disposal compare to UPW production and associated wastewater generated? So how
Yeah.
does the go? Yeah, go ahead.
Scott, you might need to repeat the second question after I answer the
Yeah,
first
no, that's
part.
fine.
So seawater electrolysis, right? So not seawater desal for making makeup water, right? Seawater direct electrolysis, right? That's the question? Or
I think they meant direct electrolysis, but I'm not positive. But
yeah, the impurities are probably the problem with that. I mean, well, see, the thing is, seawater has a lot of chloride in it, so chlorine will form. So that's why you can do chloralkali more easily. Making hydrogen from directly from seawater, getting pure hydrogen, I think, will be very challenging. Actually, no, I don't think you could pull it off. Like, I'm like revising in my mind the electrochemistry notes of which preferential reaction happens, but that would be technically difficult to do, because I think some of the other stuff might preferentially form. Again, this is I'm just thinking back to my PhD notes on this, but like that's why you need ultra pure water, like for the seawater, for electrolysis for making hydrogen. I would say, but that said, there's a different question on, can you use seawater as a feed
So
to
right.
these projects? And you can use seawater desalination. So it just makes the water treatment more costly. There's another question on here about the relative costs associated of the water treatment. Water treatment is a very small part of, let's say, overall cost for any of these projects. Right now, for brackish water treatment, we're seeing that as things get into more and more water stress regions, and you need an RO to power or to make the water for the cooling towers, we're seeing the cost trend up more. But right now, it's I would say things are maybe under 10 cents a kilogram of hydrogen, um, for brackish cases, between 5 and 10 maybe, for projects. But as you get to saltier water, it'll keep going up. So I would say that seawater desal wouldn't kick in for this until the cost of green hydrogen is reduced significantly, because then because right now the costs are high. So it wouldn't make sense to go to more costly water treatment fully, unless there's a demand driver, unless you have a big user of hydrogen there that would justify the cost, because transporting hydrogen also introduces costs. So it's a relative question there. But it'll take a while before I think you'll see large scale
No.
seawater desal driven
And we're not seeing in the market, right? We're
Yeah.
seeing the proliferation of these projects are areas that have the water, and they're green, California, Arizona, landlocked, internal. The ones in the Gulf are significant. There's plenty of water. There is some stressed water in certain regions of the Gulf, like Corpus Christi, and there's a lot of discussions about projects that are have been announced in the area. We don't see it. The technology is there, is energy intensive. You can get ultra pure water from seawater. It's not very common, and we don't see it again because of the difficulties and the challenges. The industry goes and tries to find much easier sources of water and treat that water versus going to seawater. There are some regions in the world that have no option, but also have the energy to produce it. So that's where you see desalination for water use, purification of water, and then use for industrial or even municipal use. You see it more often, more
Hmm.
common. I did see a lot of questions too about the seawater. So that's
Yeah.
typically the challenge we see.
Okay. All right. Very good. So I think we're about at the end of our allotted time here, but I'd like to just squeeze in one more question if we can. So if you can talk just a little bit more about the challenges and opportunities for and also the comparative in economics for using alternate sources of raw water, such as brackish groundwater, gray water, industrial wastewater, and so on. If you have any thoughts on that before we wrap up.
Yeah, yeah. So as the water gets more dirtier, the costs go up. So the easiest would be, let's say, municipal water to ultra pure water. Surface water to river water to that would add a little bit more cost in the need for original raw water treatment. When it gets to brackish water, the challenge we've seen is cooling water treatment drives costs because you need to meet the certain limits for the cooling towers. Industrial wastewater also, I would say the same, similar challenges might apply. You need probably need biological treatment upfront. It's all doable. Like, it's within the realm of making it happen. It's just a question of at some point the water, even though water treatment is low compared to everything else, the electrolyzers are way more expensive. But at some point that threshold will get crossed on these projects, because at the end many projects are competing for a market price that's much smaller than the cost of producing it, right? So costs are a major driver for a lot of these projects. So I would think that over time projects would first exhaust all of the easy water sources first before going to the more challenging water sources. So
All right, I think we are out of time here, so we're going to have to leave the webinar there for now. We're going to just to remind people, two quick reminders. If you haven't already, go to the handouts tab on the right side of your screen and just check out the resources there. And then secondly, the archive to this webinar will be posted after the conclusion of the webinar. It's going to be at www.chemengonline.com/webcasts. So CHEMENG online.com, and you'll be able to see a recording of the webinar. So before we wrap up, I just wanted to thank our two speakers for sharing their expertise today. And thank you to Xylem and Evoqua for sponsoring today's event. To all the attendees, thanks for listening and attending, and we hope you enjoy the rest of your day.
Thank you, everyone.
thank
Thank you,
you.
Scott. Thank you. Have a good day.
Bye.
Bye.